Okay.
Right.
Could you start with screen sharing? I mean, better full screen of the presentation.
Full screen, sorry. Yeah. Okay.
Okay, welcome everybody to today's ISGC seminar. Today's speaker is Neil Turok from the University of Edinburgh. Um, he did his PhD in 1983 at the Imperial College at the University of London. And he is now, since 2020, if I saw correctly, at the University of Edinburgh. Thank you very much for giving this talk. And as a short notice at the beginning, Neil has to leave sharp at 9
Two.
p.m. Chinese time. So
Yes.
we need to stop punctually. And with that, I immediately hand over to you. Thank you very much for giving this talk. The stage is yours.
Thank you very much, Torben, and welcome everybody. Thank you for attending this seminar. I'm going to talk about a somewhat unusual approach to cosmology, which is motivated by a very particular thought, which is that people like me have been building models of particle physics and of cosmology for several decades. Most of those models predicted signatures which have not been seen. So on the one hand, you have the Large Hadron Collider, which has seen nothing apart from the Higgs boson, which was predicted in the 1960s. And on the other hand, you have the observations of the large-scale universe, which have revealed a very surprisingly simple picture. Again, no signal of any exotic physics, of anything proposed by particle theorists or so-called fundamental theorists. And so this pattern of sort of simplicity and economy in nature really began to strike me about 10 years ago, that I wondered whether we were on the right track. Because it might be that nature has found more economical solutions to the big puzzles in particle physics and cosmology, more economical solutions than the ones we have so far appreciated. So that was the motivation for really trying to rethink everything in cosmology, trying to come up with simple, more rigid explanations. More rigid meaning more predictive, fewer parameters, fewer ad hoc ingredients and assumptions. And of course, this is difficult. Things are as complicated as they are in fundamental physics for good reasons. Superstring theory has led many people to believe in a multiverse, for example, which is probably the most complicated theory you can imagine. And these are not silly people, these are very smart people. But personally, I've chosen this route of trying to understand the extreme simplicity in nature. I should also say there are some hints of problems with minimal cosmology. So, for example, the Hubble constant tension. So far, I think these are not yet convincing, that there's not compelling evidence against the minimal description. And the line of research I want to pursue is to see maybe that minimal description is all there is. But there's still a lot of puzzles we have to resolve, and how might they be resolved within that framework. So this is work I've done with Latham Boyle, who's my main collaborator. He's recently moved from Canada to Edinburgh. He's there with me, and Megan Anderson and Sam Bateman are two students, and Franz Herzog is an expert in quantum field theory who's collaborating with us. So, to summarize, lambda CDM provides an amazingly simple description of the large-scale universe with just 5 parameters. And so it seems that the universe on large scales is really extraordinarily simple. We have, as you all know, I'm sure, cosmological constant, dark matter, and so there's a fundamental number which is conserved as the universe expands, the dark matter to baryon density, and then we have the number of baryons per photon, which tells us the baryon asymmetry of the universe. So those three numbers govern the matter or energy content, and presumably those three numbers have to come from fundamental physics. And then the geometry of the universe seems surprisingly simple as well, namely that there were primordial, approximately scale invariant fluctuations, so far consistent with Gaussian, pure scalar, so no tensor modes have so far been seen. So the way we usually describe this is by calculating the variance of the Newtonian potential, and all the Fourier modes contribute to this variance. And if ns equals 1, then this is precisely scale invariant. There's equal contribution to the variance from each log interval of wave number. But what we actually see in the observations is a slight tilt. Ns minus 1 is a small negative number, and so you get slightly stronger fluctuations as you go to larger scales or smaller k. So two numbers characterize the spectrum of fluctuations coming out of the Big Bang. An amplitude, which is about 10 to the minus 9, and the small tilt of the fluctuations, the minus 0.04. Very many quantities are observed to be zero so far. Spatial curvature, tensor modes, isocurvature perturbations, non-Gaussianity. So we really live in an extraordinarily economical universe. And so this whole talk will be to try to explain these five numbers as best we can without introducing any new particles or forces or dimensions or objects like strings or other exotica. And you'll see to what extent you believe we've succeeded. What I claim at the end of the talk is we have a new explanation which predicts these numbers, exactly this amplitude and the spectral tilt, in terms of standard model physics, standard model coupling constants. So that's really surprising. I'll also show you a new explanation for the dark matter, which I claim is the simplest possible, well, the simplest known explanation so far. It's quite economical. It wouldn't be a surprise at all if this explanation was true. And this explanation will be tested in the next 5 years. So I would claim that this evidence of extreme simplicity is something we should focus on first before introducing other complications into physics. On the very large scales, we see this pattern of CMB anisotropy, the temperature and the polarization. I was very fortunate to be the first to calculate this spectrum of polarization on the sky. And what mainly convinced me that the universe is so simple is the extraordinary agreement between this curve and the measurements. You see the bumps and wiggles at just the right place. If you fit the cosmological parameters to the temperature spectrum, this is an absolute prediction with no free parameters, and it sits perfectly on the data. And so, yeah, the physics we know from our solar system really does apply to the large-scale universe. And none of these features indicate anything beyond the physics we already know. There's no specific signature of inflation or extra particles or anything. It's all the most economical picture you could imagine. So this simplicity suggests we look for simpler and more rigid theoretical explanations, as I mentioned. And so in this talk, I'm really going to talk about what I think so far is the minimal unified framework explaining all the cosmological observations. And it's based on the minimal assumption, which is that we extrapolate the radiation back epoch and the standard model all the way back to the Big Bang singularity. We assume that there is no other forces, no other particles. There was no inflation. We just extrapolate it back to the singularity, and we try to understand how what principles lead to the observations. Our principles that we're guided by is CPT symmetry, which there's good reason to believe every possible consistent quantum field theory obeys. And so we take CPT symmetry as a basic principle which should govern the universe. Analyticity, namely if solutions of the field equations are genuine solutions, genuine solutions of the field equations are analytic, and we take what we shall find is that what I shall explain is that there's good evidence that the radiation-dominated epoch extrapolated back to the singularity was, in a certain sense, analytic, and that allows you to understand a boundary condition at the Big Bang itself. And the final one is conformal or Weyl symmetry, which is one of the most basic symmetries of nature, that you can change the local scale in physics, and the equations are invariant under that. And indeed, this conformal or Weyl symmetry is one of the few ways one can imagine of understanding the Big Bang singularity itself, which is to say that although the size of the universe shrank to zero at the Big Bang, the matter within the universe was completely insensitive to the size of the universe at that point, and so the equations governing the matter do not become singular at the Big Bang. So with these principles, we have found new explanations for lambda CDM's key features. We predict 3 generations of particles. Each one includes a right-handed neutrino. One of the right-handed neutrinos is the dark matter. There's no need for inflation or any other particles. And based on these assumptions, we explain the amplitude, tilt, and statistical character of the primordial fluctuations. Namely, they are scalar, there are no gravitational wave, long wavelength gravitational wave perturbations, and no other complications in the primordial fluctuations. So let's start with the dark matter. This idea really set us off on this route of trying to find the simplest explanation for everything. And it was a surprise to me that there is a possible explanation of the dark matter which doesn't require any new particles beyond what you need to explain the particle physics that we know. And that is right-handed neutrinos. So as you know, this is the standard model. The minimal standard model without right-handed neutrinos is extraordinarily successful, but it has this funny feature that the neutrinos only come in one-handedness. So just on basic mathematical grounds, the simplest extension you can make of the standard model is to take off that left-handed index, and then all the particles have both left and right-handed partners. That is actually needed, or it just taking off that superscript L gives you something you need, which is you have to explain the light, the masses of the observed neutrinos, light neutrinos, and mixing with a heavy right-handed neutrino is the simplest theoretical explanation we know of for those very light neutrino masses. So this is the way it works. If you take a left-handed neutrino, it couples to the Higgs and a right-handed neutrino. If the right-handed neutrino is very heavy and unstable, then it will simply decay into Higgs boson and left-handed neutrino. But this mixing of left and right gives the left-handed neutrinos a small mass. And basically, the heavier you make the right-handed neutrino, it's only created as a virtual particle in this process, and it lasts the duration of the time associated with the mixing is inversely proportional to the mass, just by dimensions. And so the heavier you make it, the less time it spends in this right-handed neutrino state before that decays, and the tinier the effective mass of the left-handed neutrino. So this naturally explains the light neutrino masses. If the right-handed neutrinos are very heavy, it's called a seesaw mechanism, because the heavier you make them, the lighter the light neutrino masses are. And this has been known for a very long time, and is perfectly consistent with all the observations we have of neutrino masses and mixings. It's also obvious from this diagram that that if you want the right-handed neutrino, so since we have three left-handed neutrinos, it's very natural to imagine there are three right-handed neutrinos for the reasons I described. And if you want one of them to be the dark matter, then you want to switch off this decay vertex. That's rather easy to do. You just impose a discrete symmetry where nu right goes to minus nu right for one of the three heavy neutrinos. That switches off this vertex. And if you do that, that right-handed neutrino is now absolutely stable. And that means that this ends up meaning that one of the three light neutrinos does not mix with the heavy neutrinos. And so one of the light neutrinos must be exactly massless. And so that's a prediction of this explanation of the dark matter, is that one of the lightest neutrino should be exactly massless, which is very interesting because that's going to be tested in the next 3 to 5 years by galaxy surveys. So how do you make a right-handed neutrino the dark matter? And this is where we started to think about the Big Bang and the Big Bang singularity and what role this played in establishing the abundance of particle species. Now, as I said, if you want this guy to be stable, you must switch off its coupling to the Higgs and the left-handed neutrinos. So it means that one of the right-handed neutrinos only couples to gravity. And for this reason, people were not able to imagine how a right-handed neutrino was created in the early universe, or what physics determined its abundance. You know, since it doesn't interact with standard model particles at all, only with gravity, what could possibly determine its abundance? So our new insight is that we realize that the expansion of the universe itself would create such a stable neutrino in a completely calculable way. That basically the expansion of the universe means that the background the neutrino travels in is time dependent, and this time dependence means that when the Hubble constant is of order its mass, so it's at very early time in the Big Bang, then these particles are created. You need to assume a particular vacuum state for the right-handed neutrino, and we chose the vacuum state consistent with CPT symmetry. So we extrapolate the Big Bang through t equals 0. We notice that there is a solution of the Einstein field equations, which is analytic at t equals 0. Only for perfect radiation fluid there is such a solution, and that solution defines the maximal analytic extension of the spacetime. So we quantize the field on this extended spacetime and work out how many right-handed neutrinos are created in this CPT symmetric vacuum. So we're able to calculate this. The answer is clear and unique, And the conclusion is that if you want these neutrinos to match the observed density of dark matter, you need the mass of this heavy stable neutrino to be 5 times 10 to the 8 GeV, which is quite reasonable. So we haven't predicted the abundance of dark matter, we're just fitting it by adjusting this parameter, which is a parameter of the standard model with right-handed neutrinos. There are other benefits of having right-handed neutrinos, one of which is that there's a very natural mechanism for generating the baryon asymmetry. This was work done before our work. It's called leptogenesis, and that is, as far as I know, the most economical way of explaining the baryon asymmetry. And this explanation of the dark matter means that the right-handed neutrinos really help in explaining both the baryon density and the dark matter density. So as I said, the stability of one of these right-handed neutrinos requires this Z2 symmetry, which switches off this vertex. And if you switch off that vertex, then this vertex also switches off. It's the same vertex. And so one of the left-handed neutrinos doesn't acquire a mass. And this is now being tested using these observations of galaxy clustering. This is the hierarchy of neutrino masses as determined by the coupling to right-handed neutrinos. So far we measure 2 mass differences using atmospheric and solar neutrinos, but the overall scale of the light neutrino masses is not known yet. And we predict that the lightest guy should be massless. And then we, depending on whether there's a normal or an inverse hierarchy, we then predict the sum of neutrino masses. So with a normal hierarchy, it's 0.06 eV, inverted hierarchy, it's 0.1 eV. This is the current data, this graph. So the peak is not very sharp, and in fact, the peak in probability with taking into account Planck and these other surveys, the peak is actually for negative sum of neutrino masses, but that which isn't allowed. But we are predicting in the case of a normal hierarchy that as the observations firm up, this peak will be well localized around 0.06. And if that's the case, then I claim that stable right-handed neutrino is easily the best candidate for dark matter. And there are other predictions which one can check with experiments, but this is the easiest one. And I think if that prediction is confirmed, then really all attention should be focused on understanding whether right-handed neutrinos are the dark matter. There's no need for any more complicated candidate. This is another experimental forecast. This is the error bar on the total sum of light neutrino masses, and the anticipated errors are about 1/5 or 20% of the predicted sum. So roughly speaking, it's a 5 sigma measurement, which is anticipated from these surveys. So that's the dark matter. Let's move on to try to understand the large-scale geometry of the universe. So of course the standard explanation is inflation, but inflation has a number of weak points. It's very model dependent. It's very dependent on assumptions about the initial conditions, which have never really been justified. There's no theory of the initial conditions, and to put it more simply, there is no measure known according to which inflation makes a flat, homogeneous, isotropic universe likely. You simply don't know the measure on the space of possible universes. And people have tried, but so far there's no connection between, there's no measure which has been convincingly applied to inflation. Inflation, of course, has many other problems, like eternal inflation and so on. So many sort of theoretical conundrums associated with it. Now, this beautiful picture by Roger Penrose, who actually I had tea with him yesterday. I'm in Oxford. And he's still going strong at whatever age he is. It's quite extraordinary. But in 1987, he published a sort of critique of inflation and why he didn't believe it. And this picture illustrates it, that the puzzle as to why the large-scale geometry of the universe is so homogeneous, isotropic, and spatially flat, you know, that's a huge puzzle. This is a very, very special geometry that we live in. And here's the creator, and he sort of picks this very special point in phase space for the universe to be in. And the big question is why, and essentially Roger Penrose said that this problem is so severe, you know, the entropy associated with all kinds of random geometries is just so large that inflation is too weak an effect to explain it anyway. But you know, that's not a widely accepted view. People, of course, love inflation because it explains the perturbations as well. So what I'm going to do very briefly in this talk is first of all explain how there is a different explanation of large-scale geometry, and secondly mention something newer, which is a new explanation of the fluctuations, which doesn't require inflation. So let's start with that. The basic idea is to say, well, do we know a measure on the space of four geometries? And the answer is that Stephen Hawking and others proposed such a measure in the context of black holes. It's a very elegant proposal. It's rather formal. Our understanding of it is still very formal. But it's very elegant and quite unique. And what we realized thinking about this and the entropy of black holes is that we could lift exactly the arguments that had been used by Hawking and collaborators for black holes. We could lift them to cosmology, and they actually give a measure on the space of four geometries. And so we were able to calculate the entropy of a cosmology. Now there, I don't want to underestimate the conceptual puzzles about this. It is a counting of states, but it's certainly not an equilibrium state. The universe is not an equilibrium. It's a full four-dimensional space-time. And what you do in this procedure is really count the number of states associated with a path in time. Yeah, it's a very interesting subject, but in a certain sense, it's the entropy of a history. It's not the entropy of a configuration. So, nevertheless, the formal trick is quite simple conceptually. You take the action for all the physics you know, including gravity, and then you go to imaginary time. So the e to the I action becomes e to the minus Euclidean action. And then you find a saddle point solution. So you find an imaginary time solution of the field equations for gravity and matter of all types. And this Euclidean configuration then gives you the entropy associated with that space-time. So there's a formal map from the partition function, which is trace e to the minus beta times Hamiltonian, to the matrix elements of the time evolution operator. And this map works if the time is imaginary. So that's what's being used. And so all you need to do to count states is to find such a saddle point and show that that saddle point is relevant to the path integral. So we managed to do this, and it's rather strange it hadn't been done before, but yeah, somehow people overlooked the fact that you could solve the cosmological equations in imaginary time actually rather straightforwardly, and therefore calculate the action and the Euclidean action, and the answer is what it is. It's unique. It's unambiguous. So just as in black hole thermodynamics, one calculates the Hawking temperature and the gravitational entropy, the simplest way to get these results is to notice that a black hole spacetime is actually periodic in imaginary time, and the period in imaginary time is the inverse Hawking temperature. And that's what this formal map between thermodynamics and quantum dynamics gives. So that's how you can derive the Hawking temperature. And then the gravitational entropy is simply the Euclidean action calculated over one imaginary time period. And in that way, you derive the gravitational entropy of a black hole. So before our work, the only example which was worked out for cosmology was de Sitter spacetime. And here you take real de Sitter spacetime, you go to imaginary time, in which case it's a sphere, and a four-dimensional sphere, and then it's very easy to calculate the Euclidean action for a four-dimensional sphere. Using the observed value of lambda, you infer that the de Sitter entropy, the entropy of de Sitter spacetime is, so this would be for an empty universe with nothing but lambda, the entropy is 10 to the 122, which is a very large number and bigger than any of the other entropies we're familiar with in cosmology, like the entropy of the radiation in our Hubble volume, for example, is about 10 to the 90. So, so this is very significant in terms of counting states of the system. So what we did is we extended this calculation of the gravitational entropy of de Sitter space, we extended it to a realistic hot Big Bang cosmology by using the fact that providing radiation dominates at early times, the spacetime is analytic at the scale factor is analytic, just has a simple zero at t equals 0. And so the universe in this case proceeds from a simple zero of the scale factor to a simple pole. The future, the blow up of the scale factor at de Sitter infinity, when when the proper time goes to infinity and the size of the universe blows up indefinitely, that future infinity is just a simple pole in the scale factor. So it's kind of remarkable that our universe, the one we actually live in, has this very simple analytical structure, that it came from a zero, a simple zero, and it is evolving to a pole, a simple pole. And we think that is actually a profound clue as to how the whole thing works and where the arrow of time comes from, for example. So I should say we continue through the Big Bang singularity. Now this is really just a mathematical device for imposing CPT symmetric boundary conditions at the Big Bang. We think of this as the method of images. So if I impose if I want to impose CPT symmetric boundary conditions at the Big Bang, what do I do? Well, one way to do it is to really try to implement some very specific boundary conditions on the metric and its derivatives and the fields at the Big Bang. But there's a more elegant way of doing it, which is the method of images, which is just to take some final boundary condition, namely an expanding universe dominated by cosmological constant, and just take the mirror image of that universe and now look for a solution of the field equations which connects those two images. And so we think of this as just implementing the method of images in cosmology, and this automatically imposes a boundary condition at the Big Bang, which is CPT symmetric. So it's just a mathematical convenience. We're not saying that the pre-bang universe is real. It's literally a mirror image of us. But in this way of doing it, you are not by hand inserting something at the Big Bang. On the contrary, you're sort of seeing what is natural at the Big Bang given the future, given the late time universe. And we think that for many reasons this makes much more sense. So it goes from a simple zero. Here are the equations for realistic cosmology. This I'm sure you're familiar with, FRW metric in conformal time. And in Planck units, the Friedmann equation just looks like this. So you have radiation, matter, space curvature, and lambda. And as soon as you write the equation this way, you realize it's just a particle in a quartic potential. And this equation was solved in the 19th century. The solution is a Jacobi elliptic function, and it's also easy to see that the only singularities in the solution of this equation are simple poles in the entire complex T plane. So the scale factor is single valued. It's also easy to see. It's doubly periodic in the complex T plane. So in the real axis, it goes from a bang to future de Sitter infinity, the blow up. On the imaginary axis, it also goes from a simple zero to a pole. And the zeros and poles form a lattice. Sorry, is there a question? No? Okay. So
Seems
on the
not.
real, okay, and on the imaginary, please feel free to jump in and ask a question. Would appreciate that. So on the imaginary axis, it's the same story. You go from zeros to poles, and in the complex T plane, there's this lattice of zeros and poles, which is periodic and happens to be rectangular for realistic cosmology. It's a rectangular lattice, and actually becomes square when the universe is spatially flat. And so the complex T plane is tiled with these rectangles. And so because of this, you can think of the solution of the Friedmann equation as a function which lives on a torus, where what I do is identify the opposite edges of the fundamental domain, and then a solution can run in T. If I move in imaginary time, the solution can run once around this torus, so it winds around the torus, and it's periodic on the torus, and therefore this imaginary time period has the interpretation of a temperature, and that is the Hawking temperature of the cosmology. And then to compute the entropy, all you do is compute the Euclidean action around this imaginary time circuit. And it turns out that by Cauchy's theorem, you see you can even deform this contour in the imaginary time direction. You can deform it in any way so that it's topologically equivalent. And by Cauchy's theorem, you get exactly the same answer. So this answer for the gravitational entropy is independent of the contour you use. It's a topological invariant. It's also independent of whatever real time you use to calculate it. So it's a number characterizing the four geometry, which, as I say, counts the number of states associated with a full four geometry, the entire cosmic history. So it's a fascinating number, and our hypothesis is that that number is indeed counting how many cosmologies there are with a certain values for these, with certain values for these parameters. So we managed to calculate this entropy analytically for general cosmology for all the conserved quantities. We treated inhomogeneities and isotropies using cosmological perturbation theory, and you can show that when you perturb this universe, then the entropy goes down. So the highest entropy universes are homogeneous and isotropic, just like the gas in a room. The most probable state is homogeneous and isotropic. It's not a puzzle why the gas is homogeneous, why the air is homogeneous in a room. It's just that is the maximum entropy state. And we claim that, likewise, it's not a puzzle that the universe is homogeneous and isotropic on large scales. When you count the states in this way, in this four-dimensional sense, then those geometries dominate. And so what I guess we were surprised to find is that this gravitational entropy does indeed favor homogeneous isotropic universes. It also favors spatially flat universes. So from this point of view, it's not a puzzle that the universe is spatially flat. Those universes have a greater entropy. And finally, this was a very nice surprise that we found out that the gravitational entropy is greatest when the cosmological constant is small and positive. And it actually doesn't make any sense. The formula doesn't make any sense when the cosmological constant is negative. It does make sense as long as it's positive, and it favors the smallest positive value. This actually echoes earlier arguments of Hawking and Coleman and others. So it's not totally original, but I think they did not really include this in a comprehensive picture of cosmology. So what we claim is that we have a thermodynamic explanation of the large-scale geometry of the universe. It doesn't require any special mechanism, such as inflation or collision of brains or other things I have worked on. I now believe those are totally unnecessary, and that understanding gravitational entropy better will explain the geometry that we see. This was a nice picture published in Quanta magazine, that if you were to pick a
Neil?
four geometry or a universe at random, then the most probable one would look like the one we see.
Neil, you have roughly 5 minutes left.
Oh, thank you. Okay, so I'm going to skip over some details because I want to get to the fluctuations. So I should say this is brand new. There are aspects of it which we don't fully understand. It's very tantalizing and it's extremely economical, but I don't want to underestimate the conceptual puzzles we still face with this explanation. So we came to this new explanation by thinking about quantum fields and gravity. When you decide to couple your quantum fields of the standard model to gravity, you immediately hit some very profound problems which have never really been solved. So this faces every theory, string theory, inflation. They all face this puzzle, and they have not. None of these approaches have resolved the puzzle. Namely, that the fluctuations of the stress energy in the vacuum are divergent. There's infinite energy in the vacuum, and gravity sees that divergence. Secondly, the basic symmetries of the theories, one of which is conformal symmetry for Maxwell and Dirac fields in 4 dimensions. This conformal symmetry is broken by the divergences of the stress energy in the vacuum. That's called the trace anomaly. So it's a very fundamental problem that the quantum regularization and renormalization ends up spoiling what we believe are very fundamental symmetries in the fields making up the standard model. So what we realized is something new, that we could cancel the vacuum energy divergence and both of the trace anomalies, the 2 independent ones, by introducing another type of field, which is rather a bizarre field, which actually has no particles. So this is the field. It's a 4-derivative field. Its canonical dimension is 0 because the Lagrangian includes d4, the action includes d4x, and then 2 powers of box, so 4 derivatives. And so phi has no dimension. It's called the dimension 0 scalar. And for this reason, it's very infrared dominated. And so it has a very red spectrum in the vacuum. So people have thought about such fields for many decades. Could they exist? What role could they play? The quantization of them is very subtle. We claim we are understanding it, but I want to mention that when you quantize this naively, you do discover negative norm states, just as you get with gauge theory. You have to project out those negative norms and then see that the surviving Hilbert space, physical Hilbert space, is positive. And we're still busy on refining that understanding. We believe it is. And we believe when you quantize it properly, you find the spectrum. See, because this field is dimension 0, the power spectrum has to be 1 over k cubed, just by dimensions. And so this dimension zero scalar has a power spectrum to lowest order, which is exactly what we see in the Newtonian gravitational potential. So the kind of minimal explanation of the fluctuations is that for some reason there are these kind of fields in the universe. They have a scale invariant spectrum, and then for some reason the Newtonian potential is proportional to this field phi. So we claim we've given an argument that indeed this is the case. So I just want to mention there's a really amazing numerological coincidence that when you calculate the vacuum energy in the standard model, you get bosons, fermions, gauge bosons. They all contribute something multiplying h bar omega over 2, the vacuum energy of a single Fourier mode. And the conformal anomalies likewise involve sums of integers with bizarre coefficients. We noticed, and this is the numerology, that all of these vanish, providing you have no dimension 1 scalars, so no normal scalars like inflatons or the Higgs boson. If they are not there, then you can have all three of these cancel exactly. And any two of the equations then predict that the number of fermions is 4 times the number of gauge bosons. This happens to be true in the standard model with right-handed neutrinos. There are exactly 12 gauge bosons and 48 fermions, which are 3 generations of 16 fermions. And then you have to have that the number of these dimension 0 scalars is 36. So for this magical number of 36 of these dimension 0 scalars, you solve all three problems, at least at free field. This is only at free field level. So I'll skip this and just tell you that if you have these dimension 0 fields and you couple them to the standard model, it turns out that they change the Friedmann equation in this way, that basically the average of these 36 fields changes the expansion rate of the universe. And so you have a local conformal scaling of the geometry, which is dependent on this field, which has very infrared fluctuations. You can actually calculate all the coefficients in terms of standard model beta functions, and it turns out you get a spectral tilt due to the running of the couplings, and remarkably, both the amplitude and the tilt agree with Planck's observations. There are a couple of additional assumptions in here which I'm glossing over, but this inference is, the assumptions we've made are in every case the simplest you can make. And big surprise, for example, was the tilt, this ns minus 1, which is minus 0.04, turns out to be minus 7 over pi times alpha QCD at the Planck scale, and this number turns out to be 0.04. So we think there is the possibility of a direct explanation of the fluctuations from very fundamental physics and from the physics of making sense of coupling quantum fields to gravity. Here's the detailed formula for the power spectrum with the tilt, and these are the actual numbers. So I'm going to skip the rest of it, which is about how these dimension 0 scalars couple consistently and so on. It's still a topic of intense interest. And so let me just summarize that we certainly have a minimal testable explanation for the dark matter, new explanation for the large-scale geometry, new mechanism to cancel the vacuum energy as trace anomalies. It also improves the graviton propagator. All this only works if there are 3 generations of fermions, each with a right-handed neutrino. It requires a composite Higgs. So for this really to work, we've got to explain the origin of the Higgs boson. And there are reasons to think it can be a composite of these dimension 0 scalars. And the same mechanism appears to quantitatively explain the large-scale perturbations. So I will stop there and welcome any questions. Thank you very
Yes,
much.
thank you very much for this nice talk.
Thank you.
Yeah, since we just have roughly 5 minutes, I would say Alejandro, just jump into it.
Hello, Neil. Thank you very much for the very nice talk. I have a
Thank
quick
you.
question about the thermodynamics argument. Like
Sure.
you say that because a flat isotropic universe has the highest entropy, this means it's most likely to have this. But
Yes.
because entropy is not necessarily constant, does this also mean that if we would start with a, let's say, non-flat universe, it
Yes.
would, with enough time, move to a high entropy state, meaning that it ends up as being flat?
So, yeah, it's a good question. So, you see, there's this fundamental in this calculation, everything is four-dimensional. Okay. So you're calculating the entropy of the entire history. And so as I mentioned, this notion of entropy is not an equilibrium notion. And in fact, gravitational entropy is never an equilibrium notion. A black hole space-time is a dynamical space-time. It's more like a waterfall than a static object. I mean, it's the entire history of the black hole. And so one shouldn't think of this entropy as increasing. It's just the whole history. And this relates to a concept. So there's a famous statistical physicist called E.T. Jaynes, who developed the sort of information theory understanding of the Gibbs-Boltzmann ensemble in the 60s. And he argued that entropy as a concept really doesn't have anything to do with equilibrium. Entropy is associated with ignorance. If you know certain macroscopic features of a system, but you don't know everything, you then try to predict what is the most likely state of that microscopic state, or states, what's the probability distribution of microscopic states for that system. And that way of thinking about entropy doesn't have anything to do with equilibrium. So I may know something about the beginning, I may know something about the far future, and then I can say what's the most likely path. And that's really more like this, what this is doing. So Jaynes invented this notion called max caliber, and the caliber is some kind of measure of the entropy of a path going from A to B. And in the last few years, this idea has become more and more kind of developed in non-equilibrium thermodynamics. And I think they're very fascinating parallels between that and gravity. So don't think about this entropy as changing. It really is the entropy of a history or a path. And it's telling you how likely are different paths. So in our case, the paths we're taking are from a Big Bang singularity, where the universe had no size, to a pole where the universe blows up in infinity. And we think that the universe, there are boundary conditions at zero and at infinity. And those boundary conditions essentially determine the arrow of time in the universe. And then you can ask, how likely is it that the interpolating geometry took, whatever form it took? And that, we think, is what this entropy is telling us. So you can only think about this entropy after you've specified the initial and the final boundary conditions.
Okay, thanks.
So it has this teleological character, you see, because we're going to a certain final boundary condition. And so we're prescribing something about the future. And of course, that's a very non-classical way of thinking about things. Classically, we think about, somebody made the universe and then it just goes where it goes, right? You just evolve it forward. But that's classical physics. In quantum physics, there's the notion of pre-selection and post-selection. And both of them are possible. In a path integral, this is exactly what you do, pre-select and post-select, and you ask what happens along the way. But yeah, it's a bit mind-bending. Yeah, it's not a sort of mechanistic view.
Okay, cool. Thanks.
So,
I would have more questions, but I think I should let someone ask.
oh, thank you. Okay.
Okay, since it's already 9, maybe just one or two short questions.
Yes, I'm very sorry to cut it off. I'm just in the middle of a workshop here, and I promised I would go back. Please feel
If
free to
there's
email me any questions. I'll do my best to answer them.
yes, or email them to us and we forwarded them to
Thank
you. That's
you.
also an option.
Thank you very
So
much.
if there are no immediate questions, then I would say we end the seminar here. Thank you very much for the nice talk and also
Thank you
taking the
all.
time during your
Oh,
busy schedule.
it's a
And
pleasure, and I hope we have a future opportunity to interact.
that would be very nice, I think, for all of us here. So then
Great.
I wish you a nice afternoon and I hope you can enjoy the workshop in Oxford.
Thank you very much. Thank you, Tobin. Thank you, everybody.
Thank you very much, Neil. Bye-bye.
Thanks. Bye-bye.
Bye. Alejandro, could you stop the recording?